Thank you everyone for coming. My name is Monica.
I'm Sophia.
I'm Havish.
And I'm Joanna.
And we're just going to be presenting on our paper, Achieving Software Quality Excellence Through Software Hardware Co-Design and Co-Verification. And it's a little about how we try to achieve software quality and ensure that through our robotics team.
All right, so a few key points and a brief overview of the content that we will be presenting today is that we're going to first have a brief explanation of what FIRST and FTC is, and then we'll go and define co-verification and co-design in FTC robotics, and then we'll go through a few case studies and end with key takeaways, a conclusion, and acknowledgements.
Well, First Tech Challenge is run by an organization called FIRST. FIRST stands for Inspiration and Recognition of Science and Technology. So the First Tech Challenge is a robotics competition that's played on a 12-foot by 12-foot playing field. Each match consists of 4 robots, and it's played in doubles, so 2 robots versus 2 robots. Each match lasts 2 minutes and 30 seconds and has a 30-second autonomous period where robots are controlled by pre-programmed um, motion, have pre-programmed motion, and then there's a 2-minute teleoperated period where drivers control the robot. So last season was center stage, and here's a short video that will recap the game rules of center stage.
Okay, so more about co-design and co-verification. There's kind of two sides to this, right? So co-design is the simultaneous development of both software and hardware. And this is really, yeah, okay.
YouTube.
Okay. Okay, thank you, Srilu. And this is where we really want to maximize the capabilities of both the hardware and software, and we want them to complement each other. And we really do this by defining what we want the robot to do and defining the robot's tasks. Co-verification is how we iterate through these designs, and this is how we really test that the software and hardware work well together, and we use advanced debugging tools that we will talk about later.
There are a few challenges when you're trying to implement co-design and co-verification in real-world implementation. And co-design and co-verification is an integral part of FTC as a whole, robotics, and as well as other high software quality. So the first integration challenge that you may face is that you need to make sure software changes can be adapted rapidly and with high quality as well. You want to make sure your software changes can be done quickly, but also keep the same high quality throughout the whole process. Additionally, you want to ensure that your hardware and software actually work well together. If your hardware doesn't complement your software, then then the software will not improve in quality at all. And just having early validation throughout this whole process makes it so much easier and is integral part of trying to adapt co-design and co-verification into the real world.
Okay, so now I'm going to go over a couple strategies for achieving good co-design that we use that you'll see throughout a couple of our case studies. Number one is SWOT analysis. So this just stands for strengths, weaknesses, opportunities, and threats. And these are 4 criteria when we're evaluating current designs or potential designs that we would like to go through. Usually we'd like to meet as a team and kind of evaluate any design. We'll go through an example for our deposition system later on. But we want to, before making any big changes in design or finalizing anything, we always want to go through just the characteristics of strengths, weaknesses, opportunities, and threats of any design. We also have our industry adapted design cycle. A big part of FTC and being in this robotics team is learning from the industry, and we noticed a couple of main steps that these industries all take while designing new products. So number one is where we start off is brainstorming. And then this is all just verbal or on paper. And we really want to create criteria for mechanisms and what makes a successful mechanism. And we use whiteboards or just talk it out just to see what we want. Number two is prototyping. We use a lot of CAD in this step, and we design on test beds. So what this means is that for 3D printed parts, we always use CAD, and then we're able to visualize what it will look like on our robot because we have a robot CAD that we keep up to date and maintained. And we also just see kind of what this new part will look like and if it's able to be built. Fabricating step, we either 3D print or we have a small CNC machine and vertical mill in our workshop where we kind of drill some holes and get a preliminary like working design of our new component. And our testing stage is we test in simulated match conditions. So we'll mount this new part onto our robot, drive around the field and see just how well it works. And we also want to iterate on our designs. And this is where we reflect back to our brainstorming step and see if we really fulfilled the criteria that we laid out for a successful design in that step. And then we just go through the cycle. So one example of this is the deposition box. So we initially started with, okay, so the deposition is basically this part in the robot that deposits the pixels from our robot onto the backdrop. And our initial deposition design was just a simple box with a latch, right? And this just allowed us to really quickly pick up the pixels and then drop them all onto the deposition system. And it works really well and was really fast at doing that one specific task, right? But then we decided that we wanted a little bit more control over what pixels we dropped and where. So if you recall in the game video, you get extra bonus points if you create a mosaic, which is a little design of 3 colored pixels. And we decided that that was actually pretty crucial to our game style. So by adding a little notch on this, a secondary notch on our preliminary notch, we're able to either lift the latch a little bit to drop just one pixel, or lift it a little bit higher to drop both at one time. And the software here was just really simple, right? We just only have to control one servo. So we just have two preset deposition positions. So our more final design, we wanted to have even more control over what pixels we drop and specifically what position we drop them in. So we figured out that choosing which pixel to drop at what time worked really well for us with the new latch design. So this time we wanted to change it up really, really big. So we decided to have a deposition system with two claws. So each claw controls one pixel. And then in addition to this, being able to drop one pixel at a time, we're also able to rotate it and pivot it up to 180 degrees each way. And then this just allowed for an extra degree of rotation
That's
in
just where it
creating.
was when we came.
Yep. Yeah. I know we would love to have it move to the front of the room.
Yeah, or we could just all change our desks.
Or we can all change our desks and have our back to the door.
It's the purpose if I have to look over my shoulder to watch it.
Yeah, I know, that's why I was like,
We
but
could really just all have this up on our computers and then be listening on headphones. That way we could even listen to whichever tracks we wanted to as well.
that's what I was wondering, like, can we have separate links or is it like, cause when I try to log on, it asks for like name and,
Yeah, that's what I did.
so what, you just put your name in as long as you have like the password or something?
Well, we're coming through. I don't know how that happened.
Perfect. So this new design just allowed us to be way much more flexible in what pixels we dropped and where and at what time. And we really saw a great score increase by doing this. And instead of just one servo, it's 3 servos working in tandem with different preset positions that just made the drivers of a robot much more efficient in dropping the pixels onto the backdrop. I would also like to use a lot of automated testing for our robot use. We want it to be like down as little as possible, right? So not only between competitions and between games, we want to do some maintenance on the robot, just make sure everything's working, ready for our next match. But also when we're mounting new parts onto the robot or just driving it around for practice in our workshop, we want to make sure that it's ready to go as soon as possible. So we have an automated tester code that detects the core reason for any malfunction the robot even might be experiencing. And the thing that I really liked about this tester code is that it tests multiple components at once. And it's so much more faster than testing manually. I'm gonna flip the robot over a little bit, as you can see. But we have 2 hubs where all of our wires are plugged into. And I think we have 12 servos and 8 motors. And you know, who knows how many sensors. But we're able to test through that in around just 4 minutes because our tester code can test multiple components at once. For example, we have a ultrasonic distance sensor on the side, as well as a limit switch, which is basically a touch sensor, just to check if our horizontal and vertical slides are all the way retracted in our robot, that we can just test at once. And we can also test entire components of the robot and individual motors and servos very easily. For example, our drivetrain are these 4 wheels down here, and each wheel is connected to a motor. So we can either test the drivetrain as a whole, or we can, if we're seeing that one wheel is having some particular issue, we can isolate that one wheel and test that.
All right, moving on to a case study about our intake. So during the season, each of the mechanical components on our robot gets refined using a synergized software hardware co-design and co-verification process to ensure precision and optimal functionality. And a key aspect of this process is the use of sensors. However, at the beginning of the season, one of the most important aspects on our robot, the intake right here, had no sensors, and we instead relied on pre-programmed wait time functions to collect pixels during the autonomous phase. And while those functions, they work temporarily, we soon realized that they weren't always accurately on time, so that sometimes made our intake collect only 1 pixel, which made us lose points, and it would even cause us to collect 3 pixels, which gave us a penalty because you're only allowed to hold 2 pixels at a time. And so our team considered using a infrared sensor to detect the number of pixels in our robot instead of pre-programmed wait time functions. However, before we cemented the idea, we used SWOT analysis to analyze and compare both components. Okay, and so here's the SWOT analysis table for the pre-programmed wait time functions. You could already see that the weaknesses and threats outweigh the strengths and opportunities. So even though the wait time functions, they don't take up any space in our robot and there's no hardware maintenance needed, as already mentioned, they cause us to lose points and it just made our autonomous very unreliable. So we thought this was not the best option for us. In comparison, here's the SWOT analysis table for the IR infrared sensor. You could already see that the strengths and opportunities outweigh the weaknesses and threats. So even though the infrared sensor, yeah, it used up more battery power, and maybe before our next competition, we wouldn't have enough time to mount it, we thought that having a very reliable, consistent, and efficient way to maximize points during the autonomous outweighed the cons. And so after we mounted the infrared sensor onto our robot, we wanted to visually compare the infrared sensor and the wait time functions. And so what we did was that we programmed 2 separate programs, one for the infrared sensor and one for the pre-programmed wait time functions. And we made our robot go and collect pixels with both of those components, and we compare the results and the consistency. You could already see that with these results that the wait time functions, they fluctuate with each trial, and it just proves that they aren't reliable and aren't consistent. And compare that with the infrared sensor, you can already see that the infrared sensor is consistent with each trial, and that proves that the infrared sensor is better and was a better choice for us. And so not only that, after we mounted the infrared sensor, we also added an LED panel to the side of our robot, which takes the output from the infrared sensor and lights up a specific color depending on how many pixels the infrared sensor detects. And so this helped our drivers make quick in-game decisions and boosted our overall gameplay performance.
Now we're going to discuss our second case study, which is movement in the autonomous period. So how does the robot move? Well, in order to move, the robot utilizes something called a drivetrain. In our case, we use a mechanism drivetrain, which means the robot has 4 wheels and 4 motors on its base. And these motors are able to put a force on the robot and make it go in whatever direction it so desires. So our this process, the mechanism drivetrain, is able to achieve holonomic movement, which means that the robot is able to go in any direction it so desires without turning or like changing its heading. So that's why we use the mechanism drivetrain. So in order to follow paths in the autonomous period, if we just have our software tell the robot where to go, this is very inaccurate, because if our robot doesn't know where it is, it has a hard time figuring out how to get to where it wants to go. So in order to improve our software's quality, we added the hardware odometry. So odometry is a method that uses these dead wheel odometry pods drivetrain. And basically what we do is, as the robot moves, these dead wheels, as we call them, will spin around, and based on how much they have spun around in a match, we are able to calculate how far the robot has gone. So these dead wheels don't actually contribute to the robot's movement, but they just track how far the robot has moved. And using this data, we are able to calculate where the robot is on the field based on its starting position and how much it has. Okay, so odometry works really well to figure out where our robot is, but in some cases we need even more precision. So we're able to implement methods of software-hardware co-verification, and using other methods such as distance sensors, we can get better estimates for our robot's position. So for example, in the autonomous period, one of our main paths is, so we start at the pixels and then we cycle to the backdrop like that, along the edge of the field. And since it's next to the field walls, you can see that um, it's very useful to have distance sensors to measure how far the robot is from the field wall. Uh, Furthermore, there's also these obstacles in the center of the field called the truss, and we don't want the robot to crash into the truss. So it's very important for the robot to have full precision in the x-axis on this field. And we can achieve that using distance sensors to measure how far the robot is on the x-axis from the wall. So this is an equation that we use to figure out how far the robot is on the x-axis from the wall. So the distance from the center, the distance from the sensor to the wall, plus the distance from the center of the robot to the sensor, times the sine theta, and theta is our robot's global heading on the coordinate field. So using this equation, we're able to figure out our distance from the wall to the robot, and this gives us a better estimate for our position on that axis. Now, distance sensors is one way that we're able to measure our position in without using odometry. But another way we can check our odometry readings with software hardware verification, co-verification, is using April tags. So April tags are a visual fiducial system, which means they're used as visual reference points along the field, and our robot is able to figure out where it is relative to those tags, and then knowing where the tag is on the field, you can figure out where your robot is. So April tags are used outside of FIRST, but they're also used quite a lot in the FIRST Tech Challenge. So they're similar to QR codes, but they store a lot less data. And then there's various April tag families. So FTC uses 36H11, which means they store 36 bytes of data and have a Hamming distance of 11, which means that if you get 11 of the digits correct, then you're able to figure out which tag it is and the tag's placement on the field. So you're able to figure out where the robot is on the field. So why would you use April tags? Well, we've determined that distance sensors are very useful on the field when you're trying to travel from the place where the pixels are located to the backdrop. But when you get to the pixels or you get to the backdrop, what do you do over there? How do you have precision to intake the pixels or to score on the backdrop? Well, we see that both the backdrop here and the intake over there, they both actually have April tags. And using these April tags, we're able to figure out where the robot is. And using software hardware co-verification, we can maintain maximum precision when intaking and scoring elements. So these are the equations for how to figure out the robot's position with the April tag. So you can do the robot's global heading is the tan inverse of delta small y over delta small x, where delta small y is the y displacement of the webcam relative to the April tag, and delta small x is the x displacement of the webcam relative to the April tag. And then the bearing is going to be an angle between the webcam and the April tag. So the delta big X, which is the x displacement of the robot relative to the April tag, is just the webcam's displacement plus the distance from the robot to the webcam times cosine of theta, which we just calculated. And it's the same thing for delta big Y, it's just delta small y, so the sensor's displacement on the y-axis to the April tag, plus the distance from the robot to the webcam times sine of theta. So we can see from these equations that the distance sensor can only give us our placement on one of the axes. But the April tags are able to give us our placement on both axes and also our heading. So they're able to give us what we call a global relocalization, which means even after a robot collides with another robot or something like that, this verification allows us to completely correct our position estimate and figure out where we are on the field. So how do you synthesize your estimates from, let's say, the distance sensors or the April tags with odometry? Well, we use the Kalman filter. So the Kalman filter is a weighted average, and it also filters out noise from the system, meaning you are able to predict the sensor's uncertainty and variance and use this in order to update your estimate. So it's a recursive model, and essentially using what you know about how closely the sensor values would be related, like, for example, the April tag and the odometry, you're able to calculate what we call a Kalman gain and add that to our position estimate in order to get a more accurate estimate based on a more accurate estimate that would represent the state better. So we performed an experiment to test how useful the Kalman filter was, and you can see that we performed the experiment once with just odometry and then no Kalman filter, and then once with the Kalman filter using a distance sensor and odometry, and you can see that. So basically, we had our robot run back and forth on the x-axis, and we measured the displacement on the y-axis after it finished running, and essentially you can see that when we use the Kalman filter, we had a lot less error on the y-axis, which strongly supports the idea that Kalman filter software hardware co-verification really improved our software quality by allowing us to follow our autonomous path spec.
The last case study we'll be going over is trajectory generation. But first, let's talk about motion profiling libraries. So these libraries are specifically designed for movement manipulation, and they do this by controlling the motion sequence of motors on a motor-based axis. And motion profiling libraries define movement in a series of steps. So if you're generating a spline, for example, there will be certain points along your spline that you pre-program and pre-select, and this just ensures the autonomous vehicle or robot moves consistently throughout your entire trajectory. Now, Roadrunner is a specifically FTC-designed motion profiling library that is designed to enable you to track your heading, velocity, and acceleration at all times on the field. Coupling Roadrunner with our odometry pods on the bottom of a robot that track our heading and position, we're able to create an accurate and efficient following path that a robot will continuously follow throughout the game. Now, how Roadrunner works is that using our odometry pods that help track our heading and position on the field, we're able to use a motion. This is a motion-based, path-based follower, right? So using a set of pre-coded instructions, and based on how long it takes the motor to turn, we're able to tell the robot where we want to go and how fast we want to achieve to that point. And this is just calculated in each path before the robot actually begins the trajectory. Now, Roadrunner has a few issues in its logic that makes it not the best choice in this scenario. So first, it's localization. So localization is used to just generate a set of instructions for a robot to follow throughout the game or the autonomous period. But Roadrunner assumes that the robot's position is correct by the end of the trajectory, and this is a huge issue. If we look at the spline on this picture here, the red points represent the trajectory points that we have pre-selected, and the yellow point represents the point of collision. If a robot at the point of collision is knocked by, for example, 10 centimeters off from its intended trajectory path, then the robot will stay 10 centimeters off the path for the entire duration of the trajectory until it reaches the very last point. And when it reaches the very last point, it will then only correct itself and remove the displacement from the original path. And this is not good because in a highly dense field, like we had last year with all the trusses and random objects on the field, if we were displaced by, for example, 10 centimeters, then we would collide into walls and we will not reach the place where we want to go. Now, Pedro pathing is a more complex path following system that was designed by FTC team Scottbots. It utilizes dynamically calculated vectors that are calculated after they reach each trajectory point. Looking at the same spline that we had before, when the robot collides with anything on the yellow point, the vector would automatically get recalculated from its position of collision, and from this, it's able to detect the displacement off the original path. Because of this and its immediate dynamically calculated vector, it knows its heading and direction, and on the very next trajectory point, it is able to fix itself and get back on the original path. And this just ensures that our robot gets to where it needs to be in the correct time and just ensures we don't hit any objects and fixes its collision afterwards. Now to reiterate, Pedro pathing is able to calculate its heading, and based on a vector, every single time you pass a trajectory point, unlike Roadrunner. And this just ensures that our consistency increases through our autonomous period, enabling a higher game score throughout the season. Now to verify that this Pedro pathing is actually better, we ran a 30-second straight line test where we drove a robot in a straight line for 30 seconds and measured the displacement of the robot from the final position to its initial position. And as you can see in the graph, Pedro pathing had significantly less error compared to Roadrunner, which verifies that Pedro pathing is the better choice for a more accurate and efficient path following system.
Okay, so now as a form of validation for our designs, we always look back on our past scores throughout our competitions in a season. So on your left is a graph of our average scores every competition that we were in, and we broke it down into its individual sections of the game, so autonomous, driver controlled, or endgame, and our total points. So there's a couple of notable things that we can see and upward trends. We added the IR sensor to the intake after League Meet 3. And after League Meet 3, we see an increase in our teleop score by a couple points. And that's pretty important because it's due to, one, scoring less penalties from intaking too many pixels or not achieving our full score potential by not intaking enough pixels into our robot, but also by adding the LED panel, we're able to show how many pixels are in our robot and what color they are. And this way, the entire team driving the robot knows what's going on inside of the robot at all times. And there's less confusion and, yelling about, what is in the robot. So there's way less confusion there. We also added Pedro pathing after League Qualifier. We saw our autonomous score was pretty level throughout all of our league meets and up until our League Qualifier. So after adding Pedro pathing and becoming a little bit more resilient to the conditions of the actual field, we're able to see an increase in the autonomous score. And then once again, we just use this score analysis as feedback and validation for the changes that you see in our case studies. So just as a conclusion, our team uses co-design and co-verification principles to ensure software quality. And some key innovations are the use of parallel processing for real-time state communication with LEDs, and that's just our IR sensor and our LED panel. We have self-adaptive localization techniques, which gave us a really big boost up in adapting to the field conditions and the other robots. And our automated testing systems to really quickly identify any errors and isolate them and fix them. So some benefits are after really, implementing these co-design and co-verification principles and following them, we really see a better control over our robot. I'm sure our drivers of the robot can all agree that it's a bit easier to control and know what's going on. There's better usability and there's optimized performance, because this is all really based on we just want the drivers to use this robot well, because even if you make the best robot design in the world, right, if it's not usable or it's very like not easily, yeah, if it's just too complicated to use, then you won't win any competitions, basically. And we also use past performance analyses as feedback and validation for software and hardware functionality. And that's the end of our presentation. We have some acknowledgements. I want to thank the PNSKC committee, especially our reviewers, Nancy Ho McCormack and Justin Wolf, for giving us a lot of helpful feedback throughout our many iterations of our paper. We want to thank our robotics team coach, Duncan Wang, for leading us, and the first program, and specifically the first program branch in Oregon, ORTOP. And we want to thank all of the FTC team coaches, mentors, and teammates that we really learned from along the way. Thank you. Do you guys have any questions? Yeah.
I noticed you have these
So yeah, we did several trials. So this would be around like 15, 20 trials. And then we just synthesized these into like different groups, like the first few and then next few, like that. So those are just like average values. And we chose that number because those we didn't expect to see more variation than like what we saw in those like 15, 20 trials. So yeah, that's how we did our experiments.
We also get a lot of feedback from our drive team because they're very quick to tell us if something's not up to their standards. But yeah, they have drivers practices like probably 5 times every week. So if there's any issues, like they're the first to tell us. So our tester code that we run is we use this driver hub just to kind of play and press play on the code. And some of the things that it runs through is that it can drive around, and then if it sees changes in the distance sensor, it'll kind of give that as positive feedback that the distance sensor value is changing as the robot is moving around. And for our limit switches, we have 2 of them, and then they just ensure that all like our robots motors aren't burning as they're constantly trying to take the slides back into the robot. And we test this by like lifting up the slides and then putting it back down and checking the limit switch for any feedback. And for the drivetrain tests, I love flipping the robot over. We kind of just drive the robot. It just drives the robot around, and then it sees if the appropriate changes or values are being received from the odometry pods. So it's just a lot of the robot doing things and seeing if it's getting back its expected value.
So to reiterate on what Monica said, there are some parts of our tester that do move components. So yeah, we like raise the slides, for example, we turn the motors or even turn the servos to just ensure they are working. But in addition, we also can get like our odometry readings as an example to see like to make sure that those wheels are working and to accurately track a position, and also just sensor readings to ensure that, oh, they're working, they're connected, and it just helps us ensure that our robot is high quality before each match.
And then so the robot will do its calculations. It'll figure out if it cleared all the tests, and then like you said, it would print out like the telemetry values on the driver. So we do have error logs that we're able to pull down on our robot. Not sure about the CPU, but I know it's an Android device. So
I think in more recent years, like the first program is trying to kind of standardize the CPUs and stuff that every team uses. So what we use right now is from the Rev brand, like not related to our team, but it's these control hubs and expansion hubs that we're able to plug the wires into, and then it's connected by a driver hub of made by the same company. I think in years past, we used to be able to use like Arduino and stuff, but I think they're trying to just get everyone to switch to Rev because it's a little bit more easy to use for all teams. Yeah. So we all kind of split up into things that we really enjoy doing. And I know like for Havish, he's like the smartest math guy I've ever met. And he really likes programming. So naturally he drifted towards that. I think I did a lot of build because I was just like, robotics. I want to build robots. I want to like get to touch all the metal. And I thought that was cool. I don't know, it's so cool.
Not really. I mean, I agree with that. Havish was definitely drifting towards the programming side. And so we kind of just talked to each of the team members and asked them, hey, what do you want to do on the team? And based off of what they want to do and what the team needs at that moment, we'll assign roles. So yeah, how we split the roles in the team.
Yeah, I think the good part about like, the robotics program that we do is that it tries to focus on more than robots. So there's an outreach division too, which I'm in, and this is where we find initiatives like PNSKC and local communities just to try and share and spread our team, First Robotics, and what we've learned throughout our years. Okay, yes. So we shall do a robot demo. You guys can come up and you guys can try driving the robot if you guys want. Yeah, of course. Okay, so this is our drive chain. We're just gonna move around, strafe around. So this is pretty good because it can strafe left and right, and it's pretty nice for moving on a relatively smaller field of 12 feet by 12 feet. And then do you guys want to intake? So now we're just intaking the pixels. And then our intake flips up. It's controlled by a couple of servos just to get that action of flipping up. And then the pixels drop down into our deposition and we can, ooh, okay. Yeah, but we're not the drive team, by the way, but yeah. Oh, do you want to try, do you know how to pivot the deposition? Yeah. Mm-hmm. Yeah. So sometimes there'll be a little pocket of where we want to deposit a pixel, and then that really comes in handy. Oh. So that was not a feature, but do I try driving the robot? Yeah. No, it's okay. And then Joanna's just driving the bottom of the robot. Wait, it literally is better than that. Okay. But yeah, that's our robot. I hope you guys learned a lot. Thank you.